welcome to this problem walkthrough. Today, we'll explore the problem titled Queens That Can Attack the King. In this challenge, we're tasked with solving a chess-based puzzle where we determine which queens can directly attack the king on a standard chessboard. Stay tuned as we break down the problem, analyze approaches, and discuss the solution. Let's get started. In this problem, we are working with an 8x8 chessboard, where both the king and a number of queens are placed at specific positions. The goal is to identify which queens can attack the king. A queen can attack the king if they are on the same row, the same column, or a diagonal, provided there are no other pieces blocking the queen's path. The input includes two lists, one for the positions of the queens and one for the position of the king. Each position is represented as a pair of integers, x, y, where both x and y range from 0 to 7, corresponding to the rows and columns of the chessboard. The output will be a list of positions for all queens that can attack the king, and the order of the output does not matter. Let's look at an example to clarify. Here, the input specifies 6 queens positioned at 0, 1, 1, 0, 4, 0, 0, 4, 3, 3, and 2, 4, and the king is located at 0, 0. In the output, we return the queens at 0, 1, 1, 0, and 3, 3, because they can attack the king. To visualize, the chessboard is shown with Q representing queens, K for the king, and .4 empty squares. The queens at 0, 1, and 1, 0 are in the same row and column as the king, while the queen at 3, 3 is positioned along a diagonal. The other queens are either blocked by other pieces or are not in a threatening position. Breaking this down further, the king is located at 0, 0. The queens at 0, 1, and 1, 0 can attack the king because they share the same row and column, respectively. The queen at 3, 3 can attack the king as well, since it lies on a diagonal that intersects the king's position. The other queens, such as those at 4, 0, 0, 4, and 2, 4, cannot attack the king because their positions are either blocked by another queen or are not aligned with the king's row, column, or diagonals. Now consider another example where the input specifies queens at positions 0, 0, 1, 1, 2, 2, 3, 4, 3, 5, 4, 4, and 4, 5, with the king at 3, 3. In the output, we return the positions 2, 2, 3, 4, and 4, 4, as these queens can attack the king. On the chessboard visualization, the queen at 2, 2 attacks diagonally, 3, 4 attacks from the same row, and 4, 4 attacks diagonally. The other queens, such as those at 3, 5, and 4, 5, are blocked or are not in a direct line of attack. Let's now consider the constraints and edge cases for this problem. The board can have up to 63 queens and 1 king, ensuring no two queens share the same position and the king's position does not overlap with any queen. For edge cases, think about scenarios such as having only one queen, the maximum number of queens, or queens whose paths to the king are blocked. Additionally, there may be situations where no queens can attack the king, or the king is surrounded by queens in all 8 directions. These constraints and edge cases ensure the problem is well defined and prepares you to handle a variety of input scenarios effectively. To solve this problem, we first considered a brute force approach. The intuition here is straightforward. For every queen on the board, check whether it lies in the same row, column, or diagonal as the king. If it does, we then verify that no other queen blocks the path between this queen and the king. The implementation of this involves iterating over each queen and performing these checks for all possible attack directions, horizontal, vertical, and diagonal. The time complexity for this approach depends on the number of queens, denoted as Q, and the average number of cells to check per direction, D. Since the board is fixed at 8x8, the worst case for D is 8, resulting in a time complexity of O(8q), which simplifies to O(q). While this method is feasible within the problem's constraints, it requires additional bookkeeping to ensure that no other queens obstruct the path, which adds complexity to the implementation. To address the inefficiencies of the brute force method, we devised an optimized approach using directional search. The key idea here is to track only the closest queen in each of the 8 possible attack directions, north, south, east, west, and the 4 diagonals. Instead of checking every cell along a path, we focus solely on identifying and updating the closest queen for each direction. To do this, we first predefine the 8 directions as coordinate offsets. Then, as we iterate through the queens, we compute the direction of each queen relative to the king and update the closest queen for that direction if the current queen is nearer. Once we process all queens, the result is a collection of at most 8 queens, those closest to the king in each attack direction. This approach is highly efficient, with a time complexity of O(q), since each queen is processed exactly once. It also requires only O(1) additional space, as we only store the closest queens for the 8 directions. This method is not only efficient but also avoids redundant checks, making it scalable and well-suited to the problem's constraints. When comparing the brute force and optimized approaches, we see clear advantages in using the optimized strategy. While the brute force method is simpler in concept, it performs redundant path checks, making it less efficient. The optimized approach, on the other hand, eliminates these unnecessary checks by focusing exclusively on the closest queens in each direction, significantly improving performance. In terms of space usage, both approaches are equally efficient, requiring only O(1) additional space. However, the optimized method offers greater flexibility. It can be adapted to handle variations in board size or movement rules more easily than the brute force approach. This adaptability, combined with its efficiency and clarity, makes the optimized approach the best choice overall. It strikes an excellent balance between computational efficiency, clarity of implementation, and scalability, ensuring it addresses the problem requirements in the most effective way possible. To solve the problem of determining which queens can attack a king on a chessboard, we start by defining the setup. The chessboard is an 8x8 grid, where each position is represented by a pair of coordinates. The queen's positions are stored in a list, where each queen is represented by its coordinates, for example, queens equals x1, y1, x2, y2. Similarly, the king's position is given as a coordinate pair, such as king equals kx, ky. The goal is to identify any queens that can attack the king, meaning there are no other queens obstructing their path along the same row, column, or diagonal. This forms the foundation of how we will approach the problem algorithmically. Now, we define the possible attack directions for the queens. A queen can attack in 8 distinct directions, horizontally to the left and right, vertically up and down, and diagonally in the top left, top right, and bottom right directions. These directions can be expressed as vectors, such as 0, -1 for horizontal left, 0, 1 for horizontal right, and so on. Collectively, these directions are stored in a list called directions, which includes all 8 possible movement vectors. To track which queen is closest to the king in each direction, we initialize a dictionary called closest_queen. The keys in this dictionary are the direction vectors, and the values will ultimately store the positions of the closest queens along those directions. This setup allows us to efficiently manage and update information as we process each queen. Next, we iterate over the list of queens to determine their relationship to the king. For each queen at position, qx, qy, we start by calculating the direction vector from the king to the queen. This is done by subtracting the king's coordinates from the queen's coordinates, resulting in dx, dy equals qx, kx, qy, ky. To ensure this direction matches one of the predefined attack vectors, we normalize it by dividing dx, dy by their greatest common divisor, or GCD. For example, if dx, dy equals 2, 4, the normalized direction becomes 1, 2. We then check if this normalized direction is one of the valid directions in our directions list. If it is, we compare the queen's distance to the king with the current closest queen in that direction. If this queen is closer, we update the closest_queen dictionary to reflect her position. By systematically processing each queen this way, we ensure accurate tracking of potential attackers. The key to solving this problem efficiently lies in a few insights. First, normalizing the direction vector is essential for accurately identifying the queen's attack direction. Without normalization, it would be difficult to determine if a queen is aligned with one of the valid attack paths. Second, tracking only the closest queen in each direction ensures that no other queens block the path, which is crucial for correctness. From a performance perspective, this approach is efficient because iterating through the queens once has a time complexity of O(n), where n is the number of queens, and updating the closest_queen dictionary takes constant time per operation. For data structures, we use a dictionary for tracking closest queens and a list to store the queen's positions, making the implementation straightforward. Finally, we consider edge cases such as when there are no queens, ensuring the result is an empty list, or when multiple queens exist in the same direction, guaranteeing only the closest one is returned. Even if the king is on the edge or corner of the board, the algorithm handles these cases seamlessly. This makes the solution both robust and efficient. This solution determines the queens that can attack the king on an 8x8 chessboard. The algorithm starts by defining all 8 possible directions in which queens can attack: vertical, horizontal, and diagonal paths. These directions are represented as pairs of changes in x and y coordinates. Next, the list of queen positions is converted into a set for efficient lookup, as checking membership in a set is faster than in a list. An empty list result is initialized to store the positions of queens that can attack the king. For each direction in the directions list, the algorithm iteratively steps from the king's position in that direction. This is done by repeatedly adding the directions x and y offsets to the current position. If the new position is outside the chessboard, x or y less than 0 or greater than 7, the loop stops. If the algorithm encounters a position that matches a queen in the queens_ set, it appends that queen's position to the result list and breaks out of the loop for that direction. This ensures that only the closest queen along each direction is considered, as any queen further along the same direction would be blocked. Finally, the result list is returned, containing the positions of all queens that can attack the king. This approach is efficient, as it processes each direction independently and stops searching as soon as a blocking queen is found. The overall time complexity is O(8*D), where d is the maximum distance the algorithm might traverse in each direction, making it highly performant given the fixed board size. Here, we begin implementing the solution in Java. First, we import the necessary utility classes. Then, we define the main method queensattackTheKing, which takes in an array of queen's positions and the king's position as inputs. Inside the method, we define all 8 possible directions that a queen can move on a chessboard. These directions are represented as pairs of changes in the x and y coordinates. Next, we convert the positions of all queens into a set. Using a set allows us to perform constant-time lookups to quickly check if a position is occupied by a queen. This is achieved by iterating through the queens array and storing each queen's position as a string in the format row column. After initializing the set, we create a list called result to store the positions of queens that can attack the king. Finally, we start iterating over each direction to explore possible movements from the king's position. For each direction, we initialize the starting position to the king's coordinates. Then, we continue moving in the current direction by incrementally updating the x and y coordinates. This movement continues until the position goes out of bounds or we encounter a queen. If the current position matches one of the positions in the queen set, it means a queen can attack the king from this direction. In that case, we add the position to our result list as a pair of integers and break out of the loop to stop further exploration in this direction. This ensures that we only consider the first queen encountered in each direction. Once all directions have been processed, we return the result list, which contains the positions of all queens capable of attacking the king. This completes the implementation of the solution. To solve this problem, we begin by defining the 8 possible directions in which a queen can move: vertically, horizontally, and diagonally. These directions are represented as coordinate offsets, like moving one step up, down, left, right, or diagonally. Next, we convert the list of queen's positions into a set to allow for constant-time lookups. This is important because as we iterate through the board, we need to quickly check if a queen is blocking the king's path in any direction. Starting at the king's position, we explore each direction step by step. For example, moving downward, we start at the king's initial position, 0, 0, and proceed to 1, 0. Since this position is in the queen's set, we know the queen at 1, 0 can attack the king. We add this position to our result and stop exploring further in this direction. Now, let's examine the next direction, which is rightward. Starting again at 0, 0, we move to 0, 1. This position is also in the queen's set, indicating that the queen at 0, 1 can attack the king. We add 0, 1 to our result and stop in this direction. Next, we consider the diagonal downright direction. From 0, 0, we move to 1, 1, then 2, 2, and finally 3, 3. Here, we find a queen in the queen's set, so we add 3, 3 to our result and stop in this direction. The remaining directions do not lead to any queens before going off the board. Therefore, the final result for this example is 1, 0, 0, 1, 3, 3. This shows which queens can attack the king from their respective positions. In the next example, we have a different setup where no queen can attack the king. The king starts at 3, 3, and the queens are positioned at 4, 4, 5, 5, and 6, 6. We initialize the same 8 movement directions and convert the queen's positions into a set for efficient lookup. As we iterate step by step from the king's position in each direction, we find that none of the positions encountered are in the queen's set before leaving the board. This means no queen is able to block or attack the king in this example. As a result, the output for this case is an empty list, indicating that no queens can threaten the king from the given positions. Finally, we examine a scenario where the king is surrounded, and queens block all possible attack directions. The king is at 3, 3, and the queens are positioned strategically to block every direction. As before, we define the movement directions and convert the queen's positions into a set. Starting at 3, 3, we move in each direction step by step. For the downward direction, we quickly encounter a queen at 4, 3, and add it to the result. Moving rightward, we find a queen at 3, 4. Similarly, moving leftward leads to 3, 2, and upward leads to 2, 3. For the diagonals, we encounter queens at 4, 4, 4, 2, 2, 4, and 2, 2. Since every direction is blocked by a queen, the final result is 4, 3, 3, 4, 3, 2, 2, 3, 4, 4, 4, 2, 2, 4, 2, 2. This demonstrates how the king is completely surrounded and unable to escape any attack path. The time complexity of our solution begins with the initialization of the queens underscore set. Converting the input list of queen positions into a set takes n time, where n is the number of queens. The reason for this is that each queen's position is inserted into the set, and set insertion happens in O1 on average. Following this, the algorithm iterates through 8 possible directions to simulate the movement of the king. In the worst case, the king might traverse up to 8 cells in a single direction, as the chessboard is 8 times 8. Since there are 8 directions, this results in a maximum of 8 times 8 is equal to 64 checks. Each of these checks involves determining if a position is in queens underscore set, which is an O1 operation. Lastly, appending up to 8 queens to the result list, 1 for each direction, also takes constant time per addition, making this step O1. When combining all these components, the overall time complexity of the solution becomes O(n). The set construction dominates the runtime, as it takes O(n) time, while the directional traversal and result processing contribute only O(1) due to their constant time operations. Now, looking at space complexity, the primary factor is the queens underscore set, which requires O(n) space to store the positions of all queens. The result list is limited to a maximum of 8 positions, 1 for each direction, making its space usage O(1). Temporary variables like directions, x, and y also use constant space. Hence, the overall space complexity of the solution is O(n), driven by the storage of the queens in the set. To understand the efficiency of the solution further, let's compare it to a brute force approach. A naive solution might involve checking all 64 cells on the chessboard. For each cell, you would check if it is occupied by a queen and whether that queen can attack the king, resulting in O64*n equals O(n) operations. This is because you would iterate over all n queens for every cell. Both the naive and optimized approaches have the same asymptotic space complexity of O(n) for storing the queen positions. However, the optimized approach significantly reduces the amount of computation by focusing only on cells along the 8 directions from the king's position. By leveraging direction-based traversal and efficient set lookups, it eliminates unnecessary checks, making it far more practical and efficient in real-world scenarios. The behavior of the algorithm can be broken down into best, average, and worst-case scenarios. In the best case, a queen is found on the very first move in each direction. This means the king performs only 1 check per direction, resulting in O(8) equals O(1) time for directional traversal. However, the overall time complexity still remains O(n) due to the set construction. In the average case, the king might traverse a few cells in each direction before either finding a queen or reaching the board's edge. The directional traversal still contributes O(1) per direction, and the overall complexity again remains O(n). In the worst case, the king traverses all 8 cells in each direction. This happens when no queens are present or all queens are at the farthest valid positions. Even in this scenario, the directional traversal contributes O64 equals O1, and the overall complexity is still dominated by the O(n) set construction. To mathematically prove the time complexity, we start with the conversion of the queens list to a set, which takes O(n) time since each of the n elements is inserted into the set. Next, the while loop simulates directional traversal. Each direction involves at most 8 iterations, and there are 8 directions, leading to O8 by 8 equals O64 equals O1 work for directional checks. Finally, appending each queen found to the result list takes O1 per addition, with at most 8 additions. When we combine these steps, the total time complexity is O(n) for set construction plus O1 for traversal and result appending, resulting in O(n). Similarly, the space complexity is O(n) for storing the queens underscore set and O1 for temporary variables, giving an overall space complexity of O(n). When solving this problem, there are several common mistakes you should be aware of. First, ignoring edge cases can cause major issues. For example, if there are no queens on the board or if the king is positioned at the edge, failing to handle these scenarios can lead to runtime errors or incorrect results. Next, diagonal checks are a frequent source of errors. To determine if a queen lies on a diagonal relative to the king, you need to compare the absolute differences of the row and column indices. This is often expressed as abs, R1, R2 equals abs, C1 EC2. Missing this condition will result in failing test cases. Another mistake is not stopping at the first obstacle in a given direction. Once you encounter a queen in a specific direction, any other queens further along that path are irrelevant, so continuing to check can lead to incorrect outcomes. Lastly, an inefficient implementation can hurt performance. For instance, iterating through all 64 positions on the board instead of focusing on the king's vicinity can unnecessarily increase time complexity. A more efficient approach would limit the search space, reducing the runtime to O1 or OK, where K represents the number of queens. Another common pitfall is hardcoding the board size. While chessboards are traditionally 8 by 8, assuming this fixed size can lead to a lack of flexibility in your solution. If the board size changes, a hard-coded approach might fail. Now, let's talk about some key interview insights. First, pattern recognition is crucial. Interviewers often look for your ability to identify symmetry and movement patterns, such as rows, columns, and diagonals. Explaining these patterns clearly can demonstrate your problem-solving skills. Additionally, optimization thinking is highly valued. While it's acceptable to start with a brute force solution, you should quickly pivot to discussing ways to reduce redundant computations, such as focusing only on valid directions from the king's position. Edge case awareness is another critical skill. Make sure to account for scenarios such as having no queens, multiple queens in the same direction, or the king being at the edge or corner of the board. Finally, consider the trade-offs between space and time. For example, pre-computing queen positions using a set can optimize lookup times, but it comes at the cost of additional space usage. Addressing these aspects during an interview can leave a strong impression. This problem is closely related to several others that you might encounter. For instance, LeetCode 51 and 52 deal with the n-queens problem, which involves placing queens on the board so that they don't attack each other. LeetCode 36, which focuses on validating Sudoku boards, also requires grid-based reasoning and is a valuable practice problem. In terms of alternative approaches, one effective technique is to use hashing for quick lookups. By storing queen positions in a set, you can achieve O1 lookup time, reducing the need to iterate through all queens repeatedly. However, this approach increases space usage, so it's important to weigh that trade-off. Another efficient method involves directional movement with early exits. Starting from the king's position, you can check in each of the 8 possible directions until you encounter a queen or reach the board's edge. This approach is highly efficient, with a time complexity of OK, where K is the number of queens, though it may feel less intuitive for beginners. Lastly, there's the brute force approach, which involves checking all queens to determine their relation to the king. While this method is straightforward and easy to implement, it's inefficient for larger inputs, with a time complexity of O(n squared). Choosing the right approach depends on the problem constraints and your familiarity with optimization techniques. That wraps up our discussion on this problem. We've covered how to determine which queens can attack the king, explored potential approaches, and highlighted key takeaways. Don't forget to practice similar problems to strengthen your understanding. Thank you for watching, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!